Hi everyone, good evening. So welcome to the third session on the Newton's laws of motion. So guys, quickly, what is it that we were covering in the second session? Second session we were looking at what are the common types of forces that we are going to be using in the context of this study of Newton's laws, or we'll say applications of the Newton's laws. Okay. So as I said, right, here we look at some common types of forces, some specific examples, right? We'll take a look at them when we'll go to the relevant problems. Okay. So already in the session 2, we have talked about the weight. So every object will experience a weight, which will be nothing but mass times the acceleration due to gravity. Okay, mass of the object times acceleration due to gravity, which will be always acting vertically downwards. Then we talked about the tension force. Tension force is the force that will exist in a tight rope or a string or a wire. Okay, so we talked about the tension force. Now today we are going to continue with the discussion, and also we talked about the spring force, the force that will exist in the spring. So we call it as the resistive force or the restoring force. What do we call it as? We'll call it as the resistive force or the restoring force of the spring. Okay. Now, whenever two surfaces are in contact, this is a very important segment. We'll study a part of it now and a part of it later. Whenever two surfaces are in contact, so there will be these surface to surface contact forces. Like in this case, you can see there is a object A and object B. These two, the surface of the object A and surface of object B, they are in contact. This is what we are calling as the contact surface. Okay, so whenever there is a contact between two objects in the contact surface, there will be two types of forces that will exist due to the contact. One is the normal reaction and other is the friction. So what are the two types of these surface contact forces? One is what we call as the normal reaction, other is the friction. First we look at the normal reaction here, and we will separately discuss about the friction in detail, because that is a little bit more elaborate study. But first understand what is the difference between the two. So when there is a contact between two surfaces, why are we not just calling it as a one force? We are saying we are dividing that into what? Two parts. We are saying one will be the normal reaction, other will be the friction. So just focus on this. This is the contact surface. So this is the contact surface, imagine. The normal reaction which we are talking about, right, will be, I mean, from the name itself, it will be normal or perpendicular to the contact surface. Like you can see here, the contact surface is what? Flat or horizontal. You see, this is what? Normal or perpendicular to the contact surface. Generally, we will represent normal reaction by the symbol N. Some textbook you will see the symbol R. Some textbooks you will see this N subscript R, like that. So all these are the notation that we use for the normal reaction. Okay, so normal reaction will be always what? It will be normal to the contact surface. Now, whenever two objects are in contact, here observe this carefully, there will be a normal reaction acting on the object A. And how it is going to be, I'll use a different marker to represent it. So the normal reaction acting on A, right, it will be from the contact surface acting into the object A. From the contact surface, it will be acting into the object A. This is what we call as the normal reaction acting on the object A. Now, how is this normal reaction coming? Because of B only, right? Because it is in touch with B, there is a force coming on A. As per the Newton's third law, for every action there should be equal and opposite reaction. Means what? This B also will experience normal reaction. and it will be what? From that contact surface it will be into B. You can see clearly on both sides the normal reaction force is going to be always perpendicular to the contact surface. And you know what will be the value of this? The value of this will be same. Why? Because Newton's third law, right? Both these action reaction pair should have equal magnitude. Both of them must be having equal magnitude. So this is the story of the normal reaction. And we'll see while solving problems, the normal reaction value can keep changing. It will not have a fixed value like that weight. Its value can keep changing. Okay. So we have seen the tension in the rope. The value of the tension force can change. If the rope is tight or very stiff, the tension force in the rope will be more. If the rope is less tight, I'm not saying the rope is slacking. Once the rope slacks, we said yesterday or the previous session, once the rope is slacking, right, tension in the rope will be what? 0. But if the rope is less tight, means tension force will be lesser. So the tension force is a variable force. Same goes with the spring also. So the spring force will depend upon what? The amount of elongation that we give for the spring or the amount of compression. Remember, the spring force magnitude is given by what? It will be given by F is equal to what? K times X. K is the spring constant. X is the amount of elongation or compression in the spring. Now the normal reaction value also can change. We'll see when we go to the specific problems, right? We'll be able to see how the normal reaction value will change. It will adjust. So this is about the normal reaction part. Now what about the other one, friction? We said we'll study about this later. But first let us try to get an idea of what this is. This frictional force, right, will be the contact force which will act along the contact plane. So how the frictional force is going to act? It will be going to act along the contact plane. So from our lower standards, if we have some idea about friction, you will know what the friction is going to do. So when there is a motion between two surfaces, right, friction will try to oppose the motion. We'll study about friction in detail later, but how the friction is going to act? It is going to be acting along the contact plane. So that is the reason why we are splitting them into what? Normal reaction, which will be perpendicular to the contact plane, and friction is going to act along the contact plane. But you know what? The initial problems we'll solve in this Newton's laws, we will consider that the surfaces are actually smooth. So when the surfaces are smooth, right, there will be no friction. When the surfaces are smooth, there will be no friction. This is the ideal case. It is not possible to have really perfect smooth surface, right? I mean, if you look at how much ever you polish, you go and see with a microscope, you will still be able to see that there will be some roughness on the surface, which means there is going to be some amount of roughness on any surface that you take. Means we cannot completely ignore friction. But since we are, of course, dealing with ideal cases with the assumption, we can say what? If the surfaces are assumed to be smooth, then there will be no frictional force acting along the contact surface. Okay, so we'll talk about friction later, and then we'll also discuss about problems where we'll have friction. Okay, so in the initial set of problems we solve, right, you will always keep seeing the statement. They'll say assume the surfaces are smooth, like that they will mention. So in all the problems wherever the friction is ignored, you will see that there will be a mention about this word saying assume the surfaces are smooth. If they want us to consider friction, then some information has to be provided. We will be able to understand what is the information that has to be provided if we have to talk about the frictional force. So when we go to the frictional force and the problems based on friction, right, we will be able to understand. So they have to give us some information, then only we can find out what is the value of the frictional force and do problems involving the frictional force. So for now, what is the assumption we are going with? We are going with the smooth surface assumption. For smooth surfaces, there will be no frictional force acting along the contact plane. There is going to be only the normal reaction. And normal reaction also can become zero. This is an important condition that we'll use while solving problems. Remember, in case of the rope, we said the tension in the rope will be zero when we cut the rope or when the rope is slacking. Similarly, the normal reaction will be zero. See, why the normal reaction is there? Because there is a contact between the two surfaces, right? Normal reaction will be zero when the contact is lost. So remember this because we'll use it while solving some specific problems. When the normal reaction will be zero, normal reaction will be zero when the contact between the two surfaces is actually lost. Okay, so this is what is the condition we will use for the normal reaction value becoming zero. So this is about the idea of the normal reaction. Now when you look at this diagram, right, like most of the students, they always think that, okay, Dinesh, hi, they always think that normal reaction will be always vertically either up or down like that. Normal reaction will depend upon what is the orientation of the contact surface. It may be vertically up, maybe vertically down, or it can have any other orientation also. For that, right, we'll just take a look at some examples. Okay, see, if you consider this one, the example that we discussed before, right? So block A, if I ask you what is the normal reaction acting on the block A, then what you will represent from the contact surface, it will be perpendicular to the contact surface. That is the first thing. So the force will be perpendicular to the surface. Okay, and if you want to find what is the normal reaction acting on A, then you know the normal reaction will be into A like this. So this is what is the normal reaction. I told you normal reaction can be represented either by the symbol R or by the symbol N. Okay, some textbooks they will represent R, some represent N. Now in this case, this is what we call as a wedge or an inclined plane. So what do we call it as? We'll call it as a wedge or an inclined plane. So look at this. Here, this is the block A and this is the wedge. Now we want to find what is the normal reaction acting on the block A. So look at this. How is this contact surface? This is the contact surface, right? That is the contact surface. Normal reaction acting on the block A will be perpendicular to contact surface. You can see how it is. It will be like this. So normal reaction need not be always vertical. It will be always what? Perpendicular to the contact surface. Now when an object, here this object A, is kept on an uneven surface. When the object is kept on uneven surface, you can see the surface below is what? It's uneven. So it is having a contact here. It is having a contact here. You can see at this contact, if you want to know what is the normal reaction acting on A means what? From the contact it will be perpendicular into A. Always when we measure normal reaction acting on any object, it will be what? It will be into that object. From the contact surface it will be into that object. Similarly, at this contact, normal reaction acting on A will be what? From the contact surface it will be into the object like that. Now if you want to know what will be the normal reaction acting on the surface, because there is an action-reaction pair of forces, right? You look at it, the normal reaction acting on the surface here will be what? Same value N1, but exactly opposite direction. Here also it will be what? Same. This side N2 means this side also N2, but exactly opposite direction, because the two normal reaction parts will be forming the action-reaction pair. That is the reason why they will be what? Equal in terms of magnitude, opposite in terms of the direction. Okay, so this understanding is what? The normal reaction can have any orientation. It need not be always vertical. It depends upon what is the orientation or how that contact surface is actually kept. Okay, now I'll show you one more example. This is another popular example that we'll use while solving some problems. Okay, like say for example you have an object. This may be a book or something. You try to hold, like you have a book in your hand, right? You try to hold the book by pushing it against the wall. So this is the wall and this is the book. You are holding it by pushing against the wall. Remember what you'll observe. If you push it slowly, like you just apply small amount of force, what do you observe? You will see that the book will actually be falling down. Maybe you can just try it at home and check. If you just hold it with a small amount of force against the wall, what do you observe? The book will be keep on sliding down. If you apply a larger amount of force, means the book will be holding there like that. Okay, now you see what is the contact surface between the book and the wall. This is the one. You can see the one that I am marking over there, right? This is what is our contact surface. This is our contact surface. Okay, if that is the contact surface, then if I ask you what is the normal reaction acting on the book, what you will say? from the contact surface, normal reaction will be what? It will be perpendicular to the contact surface, like it will be perpendicular to the contact surface, but it will be into that object. It will be perpendicular to the contact surface, but it will be into the book. So this is how we'll represent. This is what? This is the normal reaction. What is this? This is the normal reaction acting on the book. So what is this? This is the normal reaction acting on the book. Okay. So this is about the idea of the normal reaction. Okay. So normal reaction will be an important force that we will be using. So in most of the problems that we will solve, right, two forces keep coming very often, whether the others will come or not. One is weight, second will be normal reaction. Okay. So these two forces will keep coming very frequently. Okay. Now, while solving problems in laws of motion chapter, we will use this idea called as free body diagram. In short, we will call it as FBD. So I tell you what is the purpose of this FBD. The purpose of this free body diagram is it will actually help us to focus on the object or the body that we are studying. Because say we want to study the motion of an object, we want to study the motion of a body. What generally happens is this object will be connected to other things. It will be connected to a rope, it will be in contact with another surface, it may be connected to a spring. Okay, like that, it will have some connections, physical connections. The free body diagram, right, is going to represent that object or body alone without the physical connections. So this is the diagram we are going to draw. So we will draw the diagram of the body without physical connections. We will draw without showing the physical connections by representing forces only. So we will just represent whatever the forces, all the forces acting on that object, right, we will represent them without showing any physical connections. By that, what happens? We will not see that clumsy, because if the physical connections are there, right, we will be confused which force is acting, how it is acting, like that. If all the physical connections are, because physical connections doesn't matter to us, right? What matters to us? What forces are acting on the object and in what direction the forces are acting. That is what matters to us, correct? So physical connections does not matter. If there is a physical connection, let's say there is a contact surface, due to that what is going to come? Normal reaction will come. If there is a smooth surface, rough surface means friction also will come. So now remove the physical connection, just represent only the normal reaction, and if there is a rough surface means represent friction also. Like that, if you represent only the forces acting on the body by removing all the physical connections, right, we will get a neat diagram where we will see just that object and all the forces acting on the object. By that, right, it makes our job easy to study the motion of the body. So we will be able to find what will be the net force acting on the object, and by that we will be able to know how the motion of that object is going to be affected. Now what we'll do is we'll just get into the example, then we'll understand. Okay, so look at the definition of this FBD. It's a representation of the forces acting on the body without the physical contacts. It's a representation of the forces acting on the body without the physical contacts. So I want to begin with one very simple example. So there is a book of mass M. So this is the book, obviously, which is kept on the table. So there is a book which is kept on the table. Now we want to draw the free body diagram of the book. I'll show you how we'll draw it. We want to draw the free body diagram of the book. So first thing is what you know, we have to draw the book as it is. So whatever the object that is there, we have to draw as it is. Now we have to look at carefully, because we should not miss any force, because if you miss a force means gone. So we should carefully look at what are all the forces acting on the book. Okay, so here every object, because they are giving a mass of the book, right, every object will have its own weight, which will be equal to what? M into G. Already we discussed about it, which will be what? Acting vertically downwards. That is over. And there is a contact here. There is a contact between the book and the table. So at this contact, there will be a normal reaction acting on the book. You see here how I am clearly representing it. From that contact surface, normal reaction will be what? It will be acting into the book. So we will have the normal reaction represented. We'll have the normal reaction represented. Now some people will ask, sir, should the line of forces match or not? Should the normal reaction, should we represent it like this? Because the weight is represented from the center, right? Should we also show normal reaction along the same line, or is it okay if we show a little bit different? The point is, it is okay if you show even little bit sidewise if you want to ensure that both the forces are represented properly. Okay, but you know, the normal reaction is going to be also acting in a symmetric manner. The normal reaction is also going to be acting what? It will be acting in a symmetric manner. So which means we will generally tend to show the normal reaction acting along the central line of the object. We will show the normal reaction acting along the central line of the object. But if you show like this also, it is not going to be a crime. But the thing is, when we go to the next chapter means not the work energy power. When we go to the rotational motion, right, there the line of force will be very important. So the line in which the force is acting is going to be very important. So at least for the free body diagram problems, whether you show the normal reaction like this or you keep in the same line, you represent the normal reaction along the same line, okay, central line, these two will not make much of a difference. Okay, and when it goes the rotational motion, we have to be very clear about the line of force, means in which line the force is acting. So in that way, right, probably from now itself it is better that we represent normal reaction also acting. Of course it will be acting perpendicular to the contact surface, but we will show it to be acting along the central line of the object. Okay, so this we will take it as what? The free body diagram of the book. Now you check, is there any other force acting on the book? Because they didn't mention anything about the friction related aspects, right? So we'll assume here what? We'll assume that the surfaces are actually smooth. That is why we also don't consider the friction. There is a contact surface, right? We are not considering friction. Why? Because whenever we have to talk about friction, we should have some more information. What is that information? We will be able to know only when we cover the friction, because some more information has to be given if we have to consider the force of friction. Okay, so this is about the free body diagram of the book. We'll see some more examples. So let us look at here now. So we have there is a block A which is kept on block B, and the block B is finally resting on the table. We are applying a force on the block B. What is the task? Assuming the surface are smooth, like this I said, right, they'll give the conditions. Assuming the surface are smooth, draw the free body diagram for A and B. We have to draw the free body diagram for A, and also we have to draw the free body diagram for B. So first, where do we begin? Shall we start with A? We will start with the free body diagram for the A. On A, there will be weight, its own weight, which is what? WA, which will be acting from the center of the body. Okay, if you know the mass of the block, means we can tell it will be equal to what? If say for example MA is the mass of the block, then what will be the weight? MA into G. But we don't know this yet. Okay, so we'll represent it as what? Weight. Then what else is there? Look at this carefully. There is a contact between the block A and block B. There is a contact between the block A and block B, which means what? There will be a normal reaction acting on the block A from that contact, isn't it? So let us call it as what? N1. So there will be a normal reaction acting from that contact surface. It will be what? Perpendicular into block A, like that. Why am I putting N1? I will tell you. Because we are going to have one more normal reaction. We are going to have one more normal reaction, not acting on A but acting on B. Not acting on A, but it will be acting on B. See, the surface are given as what? Smooth. Means I don't think any other force acting on A, that's it. On A we have only two forces. One is the weight of A, and then the normal reaction acting between the contact surface of A and B. Now let us come to the block B. Block B will have its own weight. Block B is going to have its own weight. Okay. Then there is already one force F acting on the block B, that is represented to the right side. Look at this. Block A and block B, they have a contact, right? Block A and block B, they have a contact. Now at this contact there will be a normal reaction acting on A, and there will be also normal reaction acting on B, isn't it? As per the Newton's third law concept, equal magnitude, opposite direction. So look at this, guys. There will be a normal reaction acting on B. There will be a normal reaction acting on B because of the contact with. So I have to represent that also in the same line. Maybe the diagram is not coming very clearly. I have to represent that normal reaction N1 also in the same line, the center line of the body. Okay. Now look at this. The block B is in contact with the surface of the table. Block B is in contact with the surface of the table, means at this. So I'll just represent this only separately. So block B is in contact with the surface of the table, means at this contact there will be a normal reaction acting on the B. So normal reaction acting on B will be what? This is the table. Normal reaction acting on B will be what? Perpendicular to the contact plane, acting into B. We will call it as N2. That is why I have used N1 for the previous one. So this N2 will have a different value. I mean, I'm not saying it will have a different value. It can have a value. We don't know whether it will be same as N1 or different. Okay. So see how it is going to be in this particular representation. It will be coming as what? Vertically up. In this representation it will come as what? Vertically up. Is there any other force? No other force, right? So we have to the right horizontally there is a force F. Then vertical line there is the weight of the block B, and normal reaction N1, both are acting vertically down, and normal reaction N2 is acting vertically up. Okay. So the normal reaction part will depend upon what is the contact surface. Normal reaction is going to depend upon what is the contact surface. Okay. So make yourself comfortable, guys, while representing these free body diagrams, because there is a saying, if you are able to draw the FBD correctly, then it's like, half the problem in this Newton's laws of motion chapter will be solved. Because if you are able to get the forces correctly represented, then we will see that the next part is going to be very straightforward. So now this is something that we all practiced or seen before, that spring connected to a mass. Draw the FBD of the mass M connected to elongated spring. This is important. So the spring is what? The spring is already elongated. The spring is elongated. What the spring will try to do? It will try to go back, right? So the spring will try to pull. You can see here the spring is elongated. So the spring will try to pull the mass. We have to draw the free body diagram for the mass. Look at this, guys. This is the mass. I'll straight away go and represent the weight mg. Okay. Then there will be a spring force acting on it. Luckily here they themselves have given what is the direction of the spring force. Otherwise we have to know by looking at whether the spring is expanded. So in this case the spring is elongated or expanded. So if you elongate the spring, means spring will try to pull the object. It will try to pull the object so that spring can go back to the original length, because always the spring will try to go back to its original length. Correct. Now what else is there? You can see there is a contact between the block and the surface here, isn't it? So here also they did not mention anything about the friction parameters. Okay. So since you need to be clear, right? I'm telling you, whenever there is an friction, they will have to talk about something called as coefficient of friction. We'll learn about it later, but I just want to give the idea. So when they don't mention about this coefficient of friction, means it is a hint for us to assume that, okay, we are dealing with the smooth surfaces. Now look at it. There is a contact on the M. There will be a normal reaction acting. See how the normal reaction will be acting? From the contact surface it will be what? Perpendicular into the M. So here you see the normal reaction is what it will be. From the contact surface it will be what? Into the object. Okay. So this is how we will represent the normal reaction. Now you can check it. So is there any other force that we are missing out? No, right? Here we are ignoring friction. So friction is not considered. That's it, right? The block will experience its own weight. Because of the contact with the floor, it is having a normal reaction. And then because of the attachment to the spring is elongated. The spring will exert or create a spring force. Check it, students. That is it. So this is what is the free body diagram for the block. This is what is the free body diagram for the block. Okay. So now we'll go to the next example. So I want you guys to take some time and draw the free body diagram. So there is a cylinder here. There is a cylinder, okay, of weight W. What is the weight of the cylinder? It is given as what? W. Resting on a V-shaped groove. So you can see here, what is the groove? The groove here is actually what? It is a V-shaped. It is like this. Now as a result of it, you see there are two contact surfaces coming, one here and one over here. Here the cylinder, right, you are actually taking a side view. When you see the cylinder from the side, it looks like what? Having a circular surface. Because you know the circular surface will be what you can see, right? What is the weight? W. We have to draw the free body diagram. Now take some time and draw the free body diagram, guys. See on this cylinder, right? Obviously there will be the weight W. Maybe I'll use a different marker so that we can see clearly. So first I'll represent it here, and then I'll give a clear diagrammatic view. So look at this. So there is a weight that will be acting on the cylinder, which is what they are also giving as what? W. That will be from the center of the cylinder, it will be vertically down. Okay, so this is the weight. There is a contact surface here, right? So in this direction there will be one normal reaction. Okay. And in this contact there will be one more normal reaction. So how many normal reactions are going to be acting on the cylinder? Two normal reactions are going to be acting on the cylinder. How many normal reactions? Two normal reactions. Okay, one at this side contact surface, other at the other side. Now one thing we need to keep in mind is that the normal reaction, right, remember, so this line or this surface which is touching the cylinder is like what? It is like the tangential. Already we talked about it in the 2D circular motion. So any line that touches the circle is what? We call it as tangential. Perpendicular to tangential means what? This becomes radial. If you draw a line which is perpendicular to the tangential, it becomes what? Radial. Radial means what? That line is going to pass through the center. The line is going to pass through the center. So the left side as well as the right side, normal reactions will be acting along the line that will go through the center. Okay, it will not be very much important now, but these things will be of importance when we go to the rotational motion chapter. As I said, we have to be looking at what is the line of a force, in which line or in which direction the force is exactly acting. So we can see that's it, right? These are the forces. Now you can see the visualization. So there will be, so the free body diagram means what? Just we have to draw that object only. So we have drawn, this is what is the free body diagram of the cylinder. Maybe if you already had drawn it, you can check it. So this is cylinder. There will be weight. This side there will be a normal reaction. We are calling it as N1. The normal reaction will be acting along the line that will go through center. This side also will have another normal reaction. Due to symmetry, right? Because the cylinder is symmetric with respect to the V-shaped groove, we will see that this one and this one will be equal in terms of numerical value. Why? Because of the symmetry. Due to the symmetry, right? Because the cylinder is what? Circular. The V-shaped groove is symmetrical. Because symmetry, right? The normal reaction magnitude on both sides will be what? Same. That is something that we will discuss when we go to the problems. Because here we are only talking about what? We are only talking about how do we draw the free body diagram. Okay. So now we'll take one more example. So with this we'll conclude the free body diagram and we'll go to the next part. So let us see, guys. So block of mass M is attached to two strings. So this is the block of mass M. This side it is attached to string. Let us call it as 1. This is also another string. Draw the free body diagram of the block. So we have to draw the free body diagram for the block. So take some time and draw it, guys. What is it? You can see the block will experience its own weight. On the left side, it is connected to the rope. Remember, the tension force will be always acting into the rope. So there will be tension force acting this way. There will be also one more tension force acting along the other rope. So this rope will apply a tension force. The other rope also will apply tension force. Remember, tension force acting on any body will be always acting into the rope. Since this is a different rope and that is a different rope, tension force values could be different. Tension force values could be different. Okay. So see here. So there is a weight acting on the body, mg, and then into this rope there will be one tension. We are calling it as what? T1. I mean, for now we can just give them some notation. So this side also there will be a tension force. We are calling it as what? T2. That's it. This is what is the free body diagram of the block. What is this? This is the free body diagram of the block. Okay. So the free body diagram is a very important thing while we are going to attempt solving the questions on the Newton's laws. Now, before we actually go to the applications of Newton's laws to solve problems, we need to know about some assumptions and some considerations. So these are very important. Why? Because without these, right, we will not be able to solve the problems. So in this we are going to talk about this very important assumption that we consider. What is it? The assumption of constrained motion or connected motion. What is this? The assumption of the constrained motion or the connected motion. So what is it? We'll discuss. See, generally when we are connecting two objects, like in this case small m body and capital M body, we are connecting them by a rope. If the rope is assumed as inextensible, the rope or string is inextensible. So generally while solving problems, right, where we have objects connected by the rope or a string, it's not a spring, it's what? String, okay, or a wire, the assumption that we'll go with is what? The rope or the string is inextensible, means what? You cannot extend it. Whatever the length, let us say the length L, it is going to be as it is. You cannot extend the length. Now practically speaking, what might happen? Even the so-called rope also, you can just little bit increase the length. That is possible. But here we are going to assume that the rope cannot be changed its length at all. The rope is what? Inextensible. So whenever we are connecting two bodies with this inextensible string, what is going to happen? We will just see. So in a time delta t, let us say this block M, which is in the front, is moving by a displacement delta x. Rope cannot change the length, right? Rope cannot change the length, means what? How much ever the front side block is moving, the back side one also will have to have the same displacement. Otherwise what happens? Otherwise the rope will get extended. So here what is the assumption we are saying? Ropes cannot get extended. Means whatever the front block, the displacement, the second block or the block of mass capital M will also have the same displacement in that particular time of delta t. If it is not having, means then there is no possibility, the rope has to be extended. But our assumption is what? Ropes cannot be extended, means both of them in a given time they are going to end up having the same displacement. Then when we connect them with a rope, that cannot be extended. Okay, so they are having same displacement in a given time, means what? If you divide that displacement by the time taken, what we'll have? We'll end up having the velocities of both these blocks will be same. The velocities of both the blocks will be what? Same. Now if the velocity of m is changing at a particular rate, the velocity of small m is changing at a particular rate, the rate at which the velocity changes, right, what is it? The rate of change of velocity is nothing but the acceleration. The rate at which the velocity of that block changes is called as what? Acceleration. If the velocity of small m is changing at a particular rate, then velocity of capital M also must change at the same rate. If not, what is going to happen? Think about it. Initially, let us say both of them are having 2 meters per second, 2 meters per second. If the velocity of small m is changing at a higher rate, than velocity of capital M. It means what is going to happen? After some time you come back and see what will be the outcome. This velocity is going to be having a higher value than the velocity of the capital M. It means what? The front side block will have to move higher displacements in a given time. If that is the case, what should be happening? The rope must be getting extended, right? But our assumption is what? Rope cannot be extended. Means at whatever rate the small m velocity is changing, same rate the velocity of capital M also should change. Means what? The acceleration of the small m and capital M must be same. So if inextensible string is connecting two bodies, the magnitudes of acceleration, why am I saying magnitude? I'll tell you. So here just focus on the word magnitude, because acceleration means we'll also give the direction. It is not required that always you have to have the direction also same. I'll show you the example later. Direction need not be same, just the acceleration magnitude must be what? Same. Otherwise what we'll have the rope getting extended. Okay, but if you assume that rope is inextensible, it means if you connect two bodies by the rope, they both should have the same acceleration magnitude. Now this is going to help us in solving problems. So whenever we are having the connected bodies with a rope, right, but the bodies will be having what? They will be having the same acceleration magnitude. Okay, now let us look at this one. So this is what I was talking about. There is a, so you know what this is? This is what we will call as the pulley. What is this? This is the pulley. So pulley is something that we are quite used to. Like if you happen to visit some of these old wells, right, what you will observe? So there will be a vessel or a bucket, something like that, which will be put into the well. Okay, so this is the well, imagine, and a person standing on this side will hold the rope and he will start pulling the rope down. So when you pull the rope down, what you are going to observe? You will pull the rope down this side, other side the rope will start coming up. As a result, the vessel also comes up. Okay, so this rope or string will move across the pulley. So the rope or the string will be able to move across the pulley. That is the main purpose of pulley. Pulley will be able to do what? Pulley will be able to move a rope or a string across the pulley. So it will actually facilitate, what it does, it will facilitate the rope movement. So what the pulley will actually do? Pulley will be able to facilitate the rope movement. Okay, so this is what we'll commonly observe in the case of the well. When you're trying to take a vessel of water, a bucket of water from the well, what you will do? You will have a rope to which the bucket or vessel is attached. You will allow the rope to go through groove. So here you will have a circular kind of a thing. So this wheel will have a groove. So there will be a groove on the wheel. You will put the rope onto the groove. Okay, so and so when you are pulling the rope on one side, other side the rope will start coming up. Okay, so this is what is the pulley setup, and we will see what are some of the common assumptions we make. So we will make some common assumptions while we are dealing with the pulley. While we are dealing with the pulley, we will make some common assumptions. That also we will discuss. Okay, so look at it. So you have the small m on one side of the pulley and capital M on the other side. Both are connected by the same rope. As I explained, right, it is like the pulley will have a groove. Through that groove, the wire is coming or the rope is coming this side. It is the same rope. It is the same rope. Okay, now look at this. Since small m and capital M are connected by the same rope, imagine, I mean, this is something that we will also able to tell intuitively. Like you have small m, imagine this is a lesser mass and capital M is what? Higher mass. So what do we observe? The higher mass body will go down and the lower mass body will be going up. So rope on this side will go down and rope on the other side will be what? Going up. Okay, now if the capital M is going down, say with an acceleration a, small m is going to go upwards with the same amount of acceleration. That is why I said here, when the two objects are connected by a rope which is inextensible, the magnitude of acceleration of the masses must be same. So here, acceleration means we will think that okay, acceleration is a vector, it will have a direction. But what is the relation here? The acceleration magnitudes must be same. Directions can be different. Like in this case, what happens? Because of the way we connected, small m will be going up, capital M will be going down, because capital M is heavy mass, right? It has to go down. And small m will be lighter mass, means it will be going up. So this is what will be the connected motion. So we are connecting the objects by having what? By having an inextensible string. By having an inextensible string. Okay. So this is also sometimes called as what? Constrained motion. Why? Because we are not allowing them to have whatever accelerations they could. So both of them will be having the same acceleration magnitude. Okay. So this is what we'll consider as the connected or the constrained motion. Okay. Now we'll look at the concept of rope with regard to the tension, because whenever there is a rope, we said the rope, if it is stiff, it will be able to exert tension force on any body that is connected to it. Here the question is, if a rope like this one, this is the rope, right? It is connected to the capital M here and small m this side. So you can see capital M, if you draw the free body diagram for capital M, right, you will represent a tension here. Capital M will experience a tension. Separately, when you draw the free body diagram for the small m, on small m, what will be the direction of the tension force? Tension force will be acting on any body, tension force will be acting into the rope. Okay. The question is, will the tension acting on capital M and tension acting on small m, will these tension forces be same or different? So for that, right, if we go a little bit later into the chapter, we will even derive this, but here we will take it like an assumption. So if we have the string which is massless, so the string or rope is massless, means if it does not have a mass, then the tension in the rope will be same everywhere. The tension will be what? Same everywhere. Means you take the tension acting on the capital M, we are calling it as what? P. At this end also the rope will create a tension force, right? Here also what will be the tension force value? T. Means tension everywhere in the rope will be what? Same. Means you connect two bodies by a rope. Like this, you connect two bodies by a rope. The tension force value acting on both the bodies will be what? Same. Because for a string which is massless, tension force everywhere in the string will be what? Same. So this is an assumption which we will anyway prove it, or we will see how this result will come when we go to the applications of the Newton's laws. Okay. But if the string has got its own mass, if the string has got its own mass and the string is accelerated, if the string is having its own mass and it is accelerated, this is important. It should have the mass and it should be also what? Accelerated. Then the tension at different points will be different. So here, just make a note of it. We will see how this can be proved once we go to the applications of the Newton's law. So while we solve problems involving the applications of Newton's law, we are going to again come back and prove these two results also. So if the string is having its own mass and it is getting accelerated, if the string is having its own mass and is getting what? Accelerated, then what happens? At different points in the string or the rope, the tension force will be what? Different. Means in the same example, if they would tell that the rope is having a mass like that, if they tell like that, then when we have to represent the tension force acting on capital M, we have to take a value, say T1. When we are representing the tension force acting on small m, we will take a different value, T2. So when the string is having a mass and also it is getting what? Accelerated. We'll see the proof for this when we go to the applications of the Newton's law. Okay. So this is what is the assumption of a massless string. when the string is massless, this is generally the assumption that we will go with in most of the JEE mains level questions. Okay, so we can have JEE advanced level questions where we will consider that the string itself can be having mass. Sometimes in JEE mains questions also we can have the string to be having mass. Okay, in that case, if the string has got mass and the string is accelerated, if the string is having mass and the string is accelerated, then what we are going to have, tension at different points on the string will be what, different, like in this case. Okay, so this is an important assumption that we will have. What do we call it as? The assumption of the massless string. The assumption of the massless string. Okay, now we'll come to the last and important assumption with regard to the pulley. So we have a pulley here, we can see. Now we look at 3 cases in terms of the assumptions. All the 3 cases, right? We will see the proof. If not in this chapter, we will see the proof in the rotational motion. So look at it one by one. No, so these assumptions are important because they are the ones that will actually help us while solving problems. I said we are going to look at the proof for these assumptions. Some of them we will see this chapter, some of them we will see in the rotational motion. Now look at the first one. The first assumption is what? String and pulley both are massless. Pulley is there. There is a string that is running across the pulley like this. There is a string that is running across the pulley. Okay. String and pulley both are massless and there is no friction between the pulley and the string. What is this? String and pulley both are what? Massless. And there is no friction between them. There is no friction between the string and the pulley. In that case, you know what is going to happen? The tension on left side of the pulley will be same as tension on the right side. Okay, so the pulley will create difference where tension on the left side and tension on the right side. Will it be same or not? It would depend upon whether this pulley is having mass and there is a friction. So whether the tension on the left side and the tension on the right side, whether these two are same or not will depend upon what? It will depend upon the pulley, whether the pulley is having a mass or not and whether there is a friction or not. If there is no mass for the pulley and there is no friction between the pulley and string, then you know what happens? Tension on the left side of the pulley, which is here P, will be equal tension on the right side. And if the string is massless, right, the entire left side will have the same tension and the entire right side also will have the same tension. We can see everywhere the tension is what? Same. Let us look at the case 2. String is massless. String is massless, but pulley is not massless, means pulley is having its own mass and there is a friction. So pulley is having a mass and there is a friction. In that case, you know what is going to happen? Look at this carefully. This is the pulley, right? Tension on one side of the pulley will be different from tension on the other side. Tension on one side of the pulley will be different from tension on the other side. This derivation, right, we will see in the rotational motion. So we will not see the proof for these assumptions here. We will only be able to see the proofs when we go to the rotational motion chapter. Okay. But since the string is massless, the entire left side, you can see tension on left side of the pulley we are marking as what? T1. It will be different from tension on right side, T2. But since the string is massless, right, entire left side tension is going to be same, T1. Entire right side tension is going to be same, which is what? T2. Since the string here is massless, only the pulley is having a mass and there is a friction between the pulley and the string. That is the reason why the left side part of the pulley, tension in that part of the rope will be different from the right side part. But throughout the left side part, tension is same, T1. Similarly, throughout the right side part, tension is same, T2. Why? Because string is still massless. We will go to the case 3. This is the extreme case. String and pulley both are not massless. Means what? Both are having mass and there is also friction between them. So already we have seen case 2, right? So case 2, what did you observe? Tension on left side of the pulley will be different from tension on the right side. So this side it is say T2, that side it is what? T3. String is having a mass here. What did we say? When the string is having a mass, tension at different parts of the rope will be different, right? Means in the left side also, everywhere the tension will not be T2, it will keep changing. Okay, so somewhere it can be T1 like that. Similarly, the right side also, everywhere the tension, in case 2 you see, on the right side, everywhere tension is same. Why? Because still the string is massless, but case 3 it is not. String is having a mass, means right side also the tension everywhere will not be same, it will keep changing. Okay, so these assumptions are important while we solve problems, and as I said, we will see the derivation for this when we go to the rotation motion. Okay, see, we have to keep, it is not like, you know, we are going to learn one chapter here and then move on. The entire mechanics, at least this Newton's laws, work, power, energy, and then the system of particles with the rotation motion of the rigid body, all these things will be closely related. So we will see some of the things that we may take as an assumption here. We will see the proof for it when we go to the rotation motion. Okay, so this is what is the assumption that we will have with regard to the pulleys. Okay, so these assumptions we have to keep in mind, and with these assumptions, right, we are done with the preparation. So far what we did is we have prepared the ground, and now we have to launch. We have to launch into solving the problems based on the applications of the Newton's laws, which will continue in the next class. So just make sure that when you come for the next class, right, you go through all that we covered before, and then, you know, we'll be able to straight away get on and start solving problems. It's going to be more interesting if you are clear with the assumptions and all the things we covered before, because applications is what is the most interesting part of the laws of motion chapter. Okay, we'll start with in the next session. We'll see you.